Greetings out there in YouTube land, and welcome to our Part 5 concluding video in the Mystery Amp video series. In this installment, we're going to check all the voltages and operating conditions within our freshly completed chassis. And if it checks out, then we're going to install it in the cabinet, hook it up, and see how well it works. I think this is an excellent procedure to follow on any newly acquired amplifier, any recently completed amplifier, any recently stolen amplifier. However you acquire it or came by it, this is a good way to verify that everything within the amp is functioning properly. Step 1, with no tubes in place, I'm going to flop it over where I can gain easy access to the tube bases. I've also labeled each of the tubes to avoid any sort of confusion. I promise you, if your memory of it is from the top and you flip it over, you're liable to get confused. So mark the tube sockets on the bottom. Check that you have a 2 amp fuse in place, not a 30 amp and not a 22 cartridge, but the proper, in this case, 2 amp fuse is in place. Step 2, plug in to your trusty current limiter. If you don't have one, see my video and make one. It is an indispensable piece of equipment in any electronics workshop. Next, we're going to see if our power transformer is putting out the 3 required voltages. 5 volts for a rectifier, the high voltage for the rectifier plates, and our 6.3 volts for our tube filaments. So I set up my trusty AC voltmeter across pins 2 and 7 of the last 6 volt filament tube in the filament circuit chain. Let's turn on the amp, and we have voltage 6.75. It's going to be a little high without the tubes in place, but we do have it. Next, we check our schematic to see that the filament pins on the rectifier are pins 2 and 8. We hook up the AC voltmeter. Remember, all of this is going to be AC because we don't have a rectifier in place. Flip on the amp, 5.4 volts. Looks like that's fine. Next, we're going to hook up between pins 4 and 6 of the rectifier. This will be the high voltage output from our transformer, and it's going to be sky high. Because there's no tube in place, it may be beyond the measuring capability of your meter. Let's see what happens. Let's see. It started out too high for the meter. It dropped down to close to 700 volts. Again, no big issue that it's high because there is no tube in place. All we care about is that voltage is present. Now we'll install the rectifier tube and connect our DC voltmeter leads between where the high voltage is output, in this case from pin 2 of the rectifier to ground. Let's turn on the amp, and once again it's high, but there's no tubes drawing current. What we want to see is that we do have our high voltage DC, and we do. From this point on, we have to be extremely careful because we have charged up our filter capacitors. Now I'm going to have to discharge them using a tool that I've shown you how to make. Let's take a look at that tool. I took an old screwdriver, sharpened the tip, put a 100 ohm 10 watt resistor between the metal shaft and this wire. Wrapped it all up because if you're hanging on to this, when you touch the B+, you will end up in a stupor somewhere in an emergency room. Okay, so to the other end of the red wire, I hooked up an alligator clip. I'm going to clip this to the chassis ground and then go in and touch the positive leads of each of the filter capacitors. Okay, having done this procedure, you will see that the DC high voltage has dropped down essentially to 0. So now I can safely go in here and touch the amp. I'll only do it with one hand. I put the other hand in my pocket or in someone else's pocket or somewhere, but you only deal with this from this point on with just one hand. Otherwise, if you complete a circuit with two hands, it will not be a very memorable or pleasant experience. Okay, now we tip the chassis over and install the tubes, making sure they're in all the right sockets. Don't laugh, smarter men than you or I have put them in the wrong sockets and screwed things up, so be very careful. Install them properly. At this point, I tend to make myself a little cheat sheet. I make a large drawing of the base of each of the tubes and put the numbers for the pins that connect to the plate. Pin 3, pin 4 is the screen, pin 8 is the cathode, so that while I'm working, I don't have to look through the little number 2 font on the schematic or something like that. I've got it here clear and at hand. And what we're going to do is this. We're going to go through and measure the plate voltage of the 6N7. It has 2 plates, so that'll be pin 3 and pin 6. We're going to do the same for the 6C5, the 6V6, and the 6J7. Now in each case we're going to measure between the plate and the cathode, because what we're concerned with is the net plate voltage. So we're going to go through then and make our measurements for plate and cathode of each tube twice for the 6N7. Now that our tubes are in place, be sure you connect a speaker, a proper impedance to this amp. Now in my case I have the 8 ohm built-in ballast resistor, but you probably don't. Be sure there's a speaker connected, because from now on we're going to be putting out a signal, and actually the volume and quality of that signal is going to give us some information about our amplifier. We can now check the plate voltage in each of our amplification and phase inversion tubes. I'm going to demonstrate just one, but they're all done in the same manner. So using our tube diagram that we have here, we see that to measure the net plate voltage of our 6J7, we'll connect to pins 3 and 8, and then switch on the amp and watch as that plate voltage stabilizes. Looks to me like it's going to be in the neighborhood of around 69 volts. What we're looking for with these measurements, especially with a newly constructed amp circuit, are the voltages present, and also are they within the normal operating parameters for the tube. In both cases here we found that they are. And that's necessary when an amp circuit like this is freshly built and has never really been tested before. You need to verify that the values are correct. The amp is dead quiet. If you had 60 cycle, 120 cycle hum right now, you would probably be able to hear it. But it's very quiet. That's a good sign. So you will repeat that procedure for each of the preamp tubes and the phase inverter. Write down your values on your sheet. Now it's time to check the tube bias of the 6V6s. First, let's measure the plate voltage net between the plate and the cathode. I'm connected to pins 3 and 8 of the left hand, or as we'll see, the blue wire 6V6. Jumps up to scary territory there for a little while, and then it drops down. You see why you want your filter caps rated at like 450 or 500? Okay, this is going to drop down to around 322. Also, and I can't say this strongly enough, be sure you're draining the filter capacitors between each step and keeping the hand you're not using happily occupied in your pocket or somewhere else. Now we'll check the other, in this case the brown wire. I say that because the wires from my output transformer, the brown one goes to the right plate, blue one goes to the left plate, and to me that's a nice way to differentiate between them. But we see that it's just about identical to what the plate voltage was on the other, and that's fairly standard. Now we're going to measure the resistance between this center tap of the output transformer primary and the brown wire, and then we'll measure between that center tap and the blue wire and figure out the resistance of this half winding here of the output transformer primary and this half winding. Now with the amplifier off, be sure filter capacitors discharged between the center tap and the brown wire, 212 ohms. Viewers frequently ask me, how do I find out where the center tap is? Well, look at the schematic, and what does it say? It's red. Let's come over here, follow that red wire up to pin 2 of the rectifier. It's going to be either 2 or 8. In this case, it's 2. So that's where I'll hook my lead. Now with the amp off, the center tap lead still connected where it was for the brown plate measurement. I move the other lead over to the blue plate pin, and I see that it measures about 210.9. Okay, I always write them down. Brown to center tap, 212. Blue to center tap, 210.9. Are they different? Yes, but not by much. A lot of times they'll vary much more than this. If it's really outrageous, like 310 or something, I would figure you got a bad winding on your output transformer. But this is really close and totally acceptable. Now with our leads in that same position where we just measured the resistance between the center tap and the blue wire, change your meter to DC volts, because it will not like what happens next if it's still in resistance mode. Be sure you've changed over here to DC volts. Flip on the amp and let's measure the voltage drop across the 210.9 ohm winding of the output transformer. Again, this will take a little while to stabilize, but it looks to me like it's going to be around 9.3. Now we turn the amp off, we drain the filter capacitors, and we connect our lead for our DC volts over here to the brown plate pin. Let's see what the voltage drop is across the 212 ohm winding. Turn on the amp. Looks like it's going to be around 8.1. Now using Ohm's law, we're going to divide the voltage drop by the resistance, and we're going to get the plate current in milliamps. In this case it's 38.2 for the brown wire, 44.1 for the blue wire tube. Both of these are high. I would say I'm looking more for like 35, something like that. Let's calculate plate dissipation by multiplying this in amps, so it'd be 0.0382 times the 322 volts that we got for the net plate voltage. Plate dissipation on this tube, 12.3, not too bad. This one is high, 14.2, and those are going to be in watts of plate dissipation. Now we're going to use our common sense a little and think, what would it take to get these down both below 12? Well, if 8.1 volts of voltage drop gives us almost 12, what if we go down to around 7.8 for this tube? Okay, so we're going to drop the voltage drop from 9.3 down to around 7.8 or 8. If you don't have an adjustable bias resistor, you're going to have to change this from 250 ohms probably to, what, about 280 or 300, something like that. It's trial and error. What I did was install in series between the 250 ohm bias resistor and ground a 250 ohm pot. So I have a total now of 500 ohms possible here. Let's see, as I crank the pot up, if I can't get the voltage drop to decrease down to just below 8 volts DC. Okay, now we have moved the probe over to the blue, which was the high voltage drop wire. The amp is on and running. We've got that 9.3, in this case 9.36 volts, a drop across the winding. Let's start gradually cranking in a little additional resistance to the cathode bias resistor and get this down more like about, I'm thinking around 7.6. Isn't this easier than going to Radio Shack and trying to buy 273 ohm resistors? Okay. Let's do that. 7.7. Now let's see what the reduction in cathode bias resistance has done to our brown wire tube. As you can see, it's dropped down to what, 6.57, which is going to be biased a little cool. Now I think you see the benefit of matched output tubes. If they have the same plate current, then you can use a single cathode bias resistor to bias them both. But if you have only a single cathode bias resistor, like I do in this amp, you're going to have kind of a balancing act between the hot tube and the cool tube. Let's see what this plate dissipation calculates to be. Let's run it at about 6.6. Now, by reducing the plate current with the increase in our cathode bias resistance, we have altered the plate voltage. As the current goes down, the voltage goes up. So let's see then what our new plate voltage is for the 6v6s. It's going to be 334. Okay, we'll say 334. I will enter that now and do the calculations for the new plate dissipation. Okay, so using the revised plate voltage that we found with the increased cathode bias resistance, giving us 6.6 volts of DC voltage drop, we get 31 milliamps for the brown tube, or 10.35 watts of plate dissipation, 36.5 milliamps of plate current for the blue wire tube, 12.2 watts of plate dissipation. This one's a little warm, this one's a little cool, but in my opinion they're close enough. I think they're going to sound just fine. Do I wish we had matched output tubes? Yes, but a lot of times, I hate to tell you, when you buy them, they're not going to come out a whole lot closer than this. So let's accept this, and I think our measurements are done. So now the moment we've all been waiting for, the chassis sliding into the cabinet. Almost brings a tear to my eye. Speakers plugged in, and the screw is holding the chassis into the cabinet. Now it's time to install the back door. And of course the amp is not legit until the official name tag is installed. Back door securely in place. Let's turn it around, plug in a guitar, and see how it sounds. Before we start the sound check, I wanted to have a reality check, okay, and tell you all a big part of the reason that I quit releasing videos is that numbness and arthritis in my hands have really interfered with my ability to play the guitar. So I moved on to sort of a coarser hobby, which was working on cars and trucks. So I'm not going to be able to do justice to this amp today, but I will do my very best. Okay, I hope that's good enough. Triode input, volume is at 4 out of 10, tone is neutral. Triode input, volume is 6 out of 10, tone is neutral. I'm right up at the front of the amp right now to let you hear what the ambient noise is, and to be honest, there isn't any, which is a good thing. Pentode input, volume is 4 out of 10, tone is neutral. Pentode input, volume is 6 out of 10, tone is neutral. that was at least adequate for you to draw some conclusions. And my own observations here, listening to this thing in real life, the pentode does have a little more gain. It does seem to be a little cleaner. The triode has, of course, a little less gain and is a little warmer. Other than that, though, the difference to me was not just overwhelming. No doubt, in the hands of a really good guitarist who could push this thing to its maximum potential, the differences would be much more evident. This video ran rather long because of all the ground we had to cover, and so I'm going to forego the old truck tour. I know you're groaning and screeching and canceling your subscriptions, but let's hold off for the next video, in which we'll take a grand tour of a 1941 International truck. And I'd like to show you a couple teasers for future videos. How about this? Does it look familiar? By coincidence, shortly after I started the Mystery Amp series, I found this on eBay and bought it. We're going to take a real close look at it inside and out in a future video. When it arrived, it did not work. We will fix it and we will listen to it. And then how about this beast? I'd heard of these, but I've never laid eyes on one until I just took this one in for repairs. So once again, we're going to take a look inside and out. We're going to fix it and listen to it. And I think this will be a new experience for all of us. Here's the rear view. God only knows what's wrong with this thing, but I guarantee you it's going to be singing like an angel in a future video. So stay tuned. Well, that's about it on this video series of the Mystery Amp Part 2, in which we constructed an amp from scratch that had both a pentode and triode input stage. I hope you enjoyed it, that you found it interesting and perhaps informative, and that you will stay tuned and join Jack and me for future videos. Thanks so much for watching. Bye for now.